The goal of this presentation is to explain how modeling and simulation supports capability-based assessments. Before we can do that, we need to define the basics of modeling and simulation. When we talk about modeling and simulation, I want you to think a little outside the box and consider all the ways that we might express modeling and simulation. When you conduct an analysis, you, as the analyst, have to apply the right model and use the right level of simulation to get the right answers. Hopefully, this presentation will point you in the right direction. I am guilty. I'm guilty of being a bit myopic how I view modeling and simulation. I still find the need to pause and remind myself of the options available when thinking about models and simulation and how I'm going to apply them to my analyses. Experience shows that others tend to have a similarly narrow view of the world they're busy working into. Back when I was a wee little engineer, there weren't any books on modeling and simulation. There were a lot of technical papers and people threw around a lot of words explaining their processes. As these processes have evolved and become established, all of the words used seem to get mashed together. For most of us, we just shrugged our shoulders and executed. It wasn't a problem until we had 30 minutes to explain to some VP or colonel what we did and why it was important. There was usually a lot of arm waving and shadow puppets involved. In the early 90s, there was an effort in the DoD to consolidate modeling and simulation. The Defense Modeling and Simulation Office was created. Initially, I was very excited that modeling and simulation would have more presence, and at the time, a lot was being written about virtual simulation guiding acquisition. Being involved in a slightly different kind of mod sim, I felt offended that the contribution of constructive simulation wasn't being included in the discussion. Today, there is a lot of talk about model-based systems engineering, and like the discussions involving virtual simulation, MBSE is not the sole answer. 10, 15 years ago, Northrop Grumman was commissioned to build a replica of the Horton Brothers flying wing, the German flying wing that was flown in 1945. As I stood on the catwalk above the model shop, I marveled at the model they were building. And as I headed back to my mission modeling and simulation group, I pondered our roles in the newly minted model-based acquisition process and how many different groups claimed responsibility for modeling. A few years later, I was supporting a program whose leadership did not understand the role of modeling and simulation. All the words, pictures, arm waving, and shadow puppets available failed to convince. The program requirements were selected by a couple of old guys sitting around a table pulling numbers out of the air. As a result, I was driven to cut through all the buzzwords and confusion. I went back to the origins of operations research and traced the developments and evolution of the processes and the etymology of the words and phrases. I've put all the pieces of modeling, simulation, and analysis in perspective, and I'd like to share that with you. While analysis can trace its roots back to Archimedes, effectiveness analysis has been a cornerstone of government acquisition since the Army Corps of Engineers used cost-benefit analysis to prioritize projects in the 19th century. Operations research was a pivotal capability of military operations during World War II, and when Morse and Kimball wrote the first book on operations research, called Methods of Operations Research in 1946, they missed an important step in establishing the science. They spoke of capabilities and demonstrated examples of effectiveness, and yet did not provide a usable definition of effectiveness or distinguish effectiveness from performance. In 1965, Defense Secretary John McNamara established cost and operational effectiveness analysis as a requirement for all DoD acquisitions. In their final report, the Weapons System Effectiveness Industry Advisory Committee, which advised the action, provided a mathematical expression of effectiveness, yet did not provide a usable definition. Today, we tend to misuse the words of analysis and then find ourselves writing tomes or waving our arms to make sure we get the information we need or communicate. As scientists, engineers, and analysts, we need precision in our language. As systems engineers, we need to grasp the breadth and depth of a system and all that we as systems engineers do. We need to get the language right. What is a model? It turns out you've been using models much earlier than expected. A model is anything that helps describe something. Models include the familiar plastic variety, fashion models like Miranda, drawings, full-scale aircraft mock-ups like the space shuttle. I would venture forth to say that we're genetically wired to model. As soon as a toddler gets past scribbling, one of the first models they create is a blueprint of their family. It tells the world about mom and dad, brother and sister, pets, and where they live. The blueprint tells about how the family functions and telling whether they're happy or not. Computer models are digitized representations of the models in the analog world. There are good models and not so good models. They can represent things that exist or not. There is no implicit quality requirement in the word model. When we discuss analytic models, we refer to mathematic or physics-based models. The models can be classified as deterministic or stochastic. The model can represent steady state or dynamic conditions. We can model it as a continuous or discrete system. In a nutshell, we use models to simplify reality and understand the problem at hand. We can capture the important parts of the problem and discard the rest. We can pull apart the model and examine it one piece at a time. We can then use the model to communicate our understanding and our solution with others. Modeling and simulation is used throughout the life cycle of a program. We use it at the beginning of a project to help define our concept. We use it to validate requirements. We use it to develop the system, including the use of CAD drawings. We develop schedules to model the development process. We build scale mock-ups. We use models and simulation to test our system. We use modeling and simulation to help train the people that will use the system. We use modeling and simulation to determine when a system needs to be upgraded or replaced. People often use the terms models and simulations interchangeably. Simulations are collections of models in an executable framework. Before computers, simulations used to be accomplished with board games. Wargaming is an intrinsic part of the military culture, and much of World War II was played out in war games before being executed. We play games both as entertainment as well as training. Who would think that many of the games you play as a kid could be considered simulations? How many doctors got their start playing Doctor or the game Operation? Fire drills are live simulations. School fire drills may have low accuracy. On the other hand, firefighter training includes controlled but accurate conditions that they will likely face on the job. Next time you play Mario Brothers, realize that you're playing a simulation of Mario's world. Why simulate? When we simulate, we see the behavior and emergent behaviors of the models or elements within the simulation. We can examine each interaction and trace the cause and effect back to its roots. We can simplify and organize the complexity of the real world into a series of observable interactions. I use the term element because within the simulation, we have real systems or real people operating within the confines of the simulation. When we build the simulation, we can control or ignore seemingly unimportant aspects of the system being modeled. These might include highly variable things like weather, time of day, time of year. We can focus on the things we understand and can control. We simulate to simplify complexity. Simulations generally can be described as a range, characterized by three styles: constructive, virtual, and live. Constructive simulations typically do not involve humans or equipment as participants. These simulations can be driven by sequences of events or discrete time steps. The anticipated path of a hurricane might be constructed through application of temperature, pressures, and currents, and other weather factors. Constructive simulations can be deterministic, stochastic, or Monte Carlo. Virtual simulations typically involve humans and/or equipment in a computer-controlled setting. Time is in discrete steps, allowing integrated elements to react in real time. Flight simulators and video games fall into this category. Live simulations typically involve humans and/or equipment engaging in an activity. Think war games with soldiers out in the field or firefighters in a training facility. Time is continuous, as in the real world. Many live simulations have virtual aspects, like computer scoring of simulated weapon fire. Playing laser tag, for example, the style of simulation is not coupled to the quality or fidelity of the models contained within the simulation. A campaign analysis can be conducted with a spreadsheet, or we can execute a live combat exercise. Deterministic models or simulations are those where rules or relationships are well understood and can be reduced to a series of equations. Example given the Breguet range equation for airplanes or the two-way radar range equation. Stochastic models and simulations capture processes that are, or seem to be, random, generally used to calculate nominal performance. Example given cumulative single-shot PK. Monte Carlo models and simulations are used when there is a great deal of uncertainty about dependent interactions between the elements within the system. Here we rely on stochastic values and a roll of the dice or use of a random number generator to determine the outcome of an interaction. There are three types of quantitative analyses: performance, effectiveness, and utility. No matter how simple or complex a system is a system. The type of analysis conducted is not coupled with the size, quality, fidelity, or complexity of the system under study. Performance of a system is generally measured at a point or based on some distribution of points. When we express the values, it might be under a set of standard conditions, explicitly or implicitly stated. For example, acceleration from 0 to 60 in 4.3 seconds implies straight and level sea level on a standard day. These values might also be expressed as average values, whether it's miles per gallon or probability of kill. Understanding these values still requires understanding the assumptions that were made. I still have trouble with the prediction of a 20% chance of rain. Effectiveness is a higher level of analysis. It requires making assumptions about the environment the system operates in and how that system interacts with the environment. Here, too, there is still no requirement of size, fidelity, or accuracy requirement that makes an effectiveness analysis an effectiveness analysis. When expressing the results, we express the results as numbers, not as averages. Averages and percentage tend to mask their meaning. For example, I can detect 100% of missile A and only 50% of missile B. It is not exactly the same as saying I detected 1 of 1 missile A and 50 out of 100 of missile B's launched. Utility is yet a higher level of analysis that addresses the full scope of operations of the system. The earliest reference found for military utility is in 1965, when Secretary of Defense John McNamara told President Lyndon Johnson that nuclear weapons have no military utility. I think there's no doubt that nuclear weapons meet performance goals and may indeed be effective. However, the cost of cleanup and the consequences of their use outweigh any benefit. Hence, the conclusion that military utility must include all aspects of ownership. This would include deployment, training, maintenance, operational use, disposal, etc. Like effectiveness measures, utility results need to be expressed as numbers of things. The bottom line is, the type of analysis employed is based on the objectives of the analysis, not the size of the system. One point I'd like to stress is that performance and effectiveness are not the same thing. The relationship between performance and effectiveness is generally nonlinear. Of course, we're all familiar with the cost-performance relationship. It costs more for each incremental improvement in performance. The knee in the curve is where we get the most bang for the buck. You may notice this when you buy a big screen TV. When you buy a TV from 20 to 55 inches, you're talking about a price of about $50 for each extra inch of TV. But as you cross some threshold around 50 inches, expect to pay $150 for each extra inch. In the example here, if we design a sensor, we start with an assumption that there is a uniform distribution of targets within the field of view of the sensor. A cheap sensor will see some of the targets within the field of view. As we build a better sensor, we can expect to pay more. And at some point, to see the last little bit of things to be seen, it's going to cost significantly more. Most sensors don't have a uniform performance across the field of view. Your eyeballs, for example. If you have a non-uniform distribution of targets within the field of view, they probably won't end up in the sweet spot of the field of view. So performance is less effective for each dollar of performance you paid for. Now, if we compare performance versus effectiveness, dollar for dollar, you can see the relationship. In this case, the cost of the added performance did little to have an effect on the ground. Let's take a look at another example of the difference between performance and effectiveness. We'll have a race. I'll give you a Maserati, a great car with outstanding performance and system attributes. 0 to 60 in 4.7 seconds and a top speed of 185 miles an hour. I'll take a simple everyday horse. 1 horsepower, top speed about 45 miles per hour, but I get to pick the race course. I choose a race to the bottom of the Grand Canyon. Which system will be more effective under these operational conditions? Who will win? Obviously, the horse wins. This might look familiar to you. In 1994, the hierarchy of models and simulations made its first appearance. The military operations research community found it warmly familiar and adopted it as the modeling, simulation, and analysis pyramid. This is a recreation of the original presentation. The original pyramid divided analysis into 4 levels: engineering, engagement, mission, and theater. The pyramid was based on the taxonomy of computer models in use by the U.S. Air Force at the time. The model applied to analysis has several major shortcomings. First, it does not easily apply to the analysis of non-shooting systems. It has difficulty describing where performance ends and effectiveness begins. There's an implication that the kind of modeling is based on the size of the system, and there's an implication that the fidelity, accuracy, is dependent on the size of the system. This leads to a great deal of confusion regarding the types of analysis required to arrive at good decisions. Everything we have discussed up to this point stands in contrast to the claims shown here. We need a new modeling, simulation, and analysis pyramid. The replacement model must be capable of addressing any kind of architecture, and it must be applicable to combat, surveillance, education, business, or medical studies. The new model must be consistent with current systems theory. More importantly, a replacement model must be usable for acquisition, requirements allocation, requirements decomposition, and test. We want to capture the essence of the definition, levels, types, and styles of modeling, simulation, and analysis that we've covered so far. A system under study is defined by its system's attributes, i.e., its physical characteristics and functional relationships. The physical description might include mass, size, color, engine size, fuel capacity, sensor sensitivity, sensor resolution, etc. The architecture documents the system. Depending on the maturity of the concept and the fidelity of the analysis, architecture might only contain an overview concept. A more mature architecture might describe the relationship of the system's components or the relationship of the system to other systems in a systems of systems architecture. The foundation layer of the new pyramid is performance analysis. We can use a back-of-the-envelope calculation as the constructive model for performance. We can scale the full range and conduct a live experiment. The output from the performance analysis are measures of performance, or MOPs. A measure of performance is one or more select measurements that show compliance with design objectives or distinguish similar concepts. Once upon a time, when computers with 64K of memory used to take up whole rooms, we would build tables of performance. That drove the next layer of the pyramid, the effectiveness analysis. Today, with 4th and 5th generation languages, gigabytes of memory, and terabytes of disk space, we federate high-fidelity models into our mission-level models that support the effectiveness analysis and drive these models directly with the architecture. The effectiveness analysis is supported by vignettes from an agreed-upon scenario, which are selected to represent the operational environment. The notation of scenario-based analyses are contained within the green triangle. The operational environment includes concept of operation, levels of training, availability, and reliability. And the key output from effectiveness analysis are, of course, measures of effectiveness. These are measures that directly support the mission goals of the system under study. These allow us to compare apples and oranges. For example, if the mission goal is moving people from point A to point B, we can use the measure passenger miles to compare autos, ships, trains, or airplanes. The next level of the pyramid is the utility analysis. This is often partly analyzed with the use of a campaign model. The utility analysis is supported by the defined scenarios. Additional analysis may be required to account for things like training and disposal of the system. The additional analyses are required if these distinguish one system from another. Remember, these are comparative analyses. The output of utility analysis are measures of objectives, or MOOs, which is a comparative measure of effectiveness of a system in an operational environment towards achieving large-scale objectives. Then you have other supporting analyses and models that ultimately tie into the architecture and support the decision processes. What do we gain from conducting modeling, simulation, and analysis? We have an increased understanding of even very complex systems. We have a way of reducing risk. We have better documentation of the system and the reasons for the decisions made. Ultimately, modeling, simulation, and analysis reduces cost. We can see the likely outcomes of alternatives in our calculations and our simulations before building the actual system. ms&a are powerful tools, and every power tool needs a warning label. Every model is limited by the assumptions that created it. Even the best models don't predict the future. They can tell you what will likely happen with some level of risk associated with it. As analysts, understand the systems being analyzed. Understand the assumptions and limits of the models and the environments. Understand what you need to analyze, then choose the tools. Don't let the tools choose the analysis. Be honest in the analyses you conduct. Don't change the Earth's gravitational constant because it's the only way of making some VIP's concept work. Provide honest answers. Let the decision makers make the decisions based on the knowledge you are responsible for providing. In the previous section, we established an understanding of what models, simulations, and the kinds of analysis they're used for. This is about what we model. The reason many of us perform modeling, simulation, and analysis is in support of the government acquiring stuff. The DoD has a prescribed method of how they acquire systems. The process relies on architectures to define the systems. Architecture is required for all IT systems and systems that incorporate IT, which is almost everything. This isn't a course in systems engineering or architecture. This is to familiarize you with the words and phrases that are tossed around during a contracted analysis. This would include the development planning or DP study, doctrine, organization, training, material, leadership, and education, personnel, and facilities, concept of operation development, analysis of alternatives, and military utility analysis. The first multi-use word commonly used and confused is the word system. You need to define what you mean when you talk about your system. A system can be anything from a doorstop to a transit system. Companies manufacture and sell systems. One company's system is another company's subsystem. And when it comes down to it, a system of systems is nothing more than a system. Knowing specifically which system you're referring to is important. Take the Space-Based Infrared Satellite System, or SBIRS. SBIRS refers to the Geosynchronous Orbit Satellite, the Highly Elliptical Orbit, or HEO satellite, the Low Earth Orbit Satellite. It was used to describe a constellation of SBIRS satellites, which may or may not have included DSP satellites. It may or may not have included the ground support systems. It also referred to the enterprise as well as the contract. Architecture, too, means many things to many people, and for some it is nothing more than a buzzword thrown about and misused. From the analyst perspective, architecture is a model of the system. And when people talk about model-based acquisition, they're talking about the architecture. JCIDS is the procedure by which the DoD buys stuff. The DoDAF is an architecture framework required for all IT programs and programs that incorporate IT. All complex military equipment contain information technology. The framework defines the information required and the format for that information. Each architecture database includes pictures, charts, dictionaries, and lists that define the physical and functional characteristics of a system. JCIDS, coupled with DoDAF, defines the model-based acquisition system process. The architecture database is the model. The concept of the model-based systems engineering, or MBSE, is another way of representing the physical or functional characteristics of the system. MBSE replaces document-based representations of a system. Documents can be generated as a view of the architecture, and as the system grows more complex, it's believed that MBSE will provide the facilities and structure that enable these systems to be more reliably engineered. The benefit of MBSE is that as a system and the architecture evolve, ripple effects as a result of changes to the architecture can be detected when the changes are made, reducing the number of surprising effects that often are not realized until much later in the program. Relationships are modeled early and maintained through the life of the database. Associated with MBSE is SysML, and not unlike XML, SysML is a schema optimized to capture and store the model of the system. SysML has predefined structures as objects that describe the complex relationships within the system. The architecture tool actually does the work of displaying and communicating various views of the data captured. There is a kind of simulation that directly utilizes the architecture database, the executable architecture. Executable architectures are, generally, performance-based simulations that are easily subjected to tractable use cases. While not restricted to being performance-based, every system that competes in a simulation should be modeled to the same level of accuracy and fidelity. If we use the architecture of an F-35 in a combat model to measure effectiveness, every other airplane would need its own architecture developed to the same level of completeness, a daunting task. Remember, every model is a simplification of reality. Models are built to satisfy a particular need. One point I'd like to stress is that modeling and simulation has always been the heart of systems engineering. It goes far beyond what MBSE is defined as. In particular, if I had to place executable architectures in a context with our discussion of M&S, I envision it here. Let's talk a little more about analysis and how it is used or should be used in acquisition. Back to our system engineering V. Most discussion about the V take place after the requirements have been defined. The greatest challenge for an analyst is at the earliest stages of the design process. Here we need to identify and validate needs and ultimately establish requirements. We need to establish concepts of operation and build architectures that might meet all the needs. We need to advise decision makers of the best course of action. Failure at this stage of the process dooms a program down the line when halfway into a program you can't meet unrealistic requirements, budgets, or schedules based on these initial analyses. Modeling and simulation facilitate these analyses and control the risks associated with the technical requirements, cost, and schedules. We identified 3 types of analysis. Let's talk a little bit about how these analyses are used. Military utility analyses are usually conducted with campaign-level simulations. Utility analysis is best conducted for trade-offs between different missions. It is especially useful for systems that have multiple missions. All systems start with a concept that is derived from one or more missions. Effectiveness analysis using mission-level analysis simulation allow us to explore mission space. It provides flexibility to assess completely disparate ways of fulfilling mission needs. Once requirements are established, we use performance analysis and models to design systems that meet requirements. We can use performance models, all things being equal, to compare systems. We can also use performance analysis to decompose system-level requirements to subsystems. Performance models also help meet requirements while constraining costs. The earliest references in military operations research and systems analysis referred to capabilities. A capability is any combination of attributes, performance, and effectiveness or utility that describes a system. It was the only term used until 1965, when the vocabulary started to become muddled. Let's talk a moment about stakeholder needs. Most engineers do not know how requirements originate. The current literature is rife with the use of the phrase stakeholder requirements. Even the Defense Acquisition University makes requirements and needs synonymous. Stakeholders include everyone involved in a project or product: decision makers, contractors, engineers, vendors, transportation people, end users, etc. More than likely, each group of stakeholders has competing and conflicting needs. Stakeholders do not usually come with requirements in hand. They more often have needs and wants. In the early stages of development, any requirement that is easily traded to save a couple of bucks or optimize another part of the design was not a requirement. We can identify a potential gap and prioritize needs, preferably with a quality functional deployment or QFD analysis. This sets the stage to validate the mission need and confirm that the gap can be closed to some degree. Once validated, the mission need becomes a mission requirement. So what is a requirement? The Space and Missile Command System Engineering Handbook has the best description of requirements. If we have a transportation requirement, most people do not purchase the vehicle with the best performance specifications, as we saw in the horse race earlier. We purchase a vehicle that best gets the job done within our budget. We purchase what we each perceive to be affordable. A requirement is a validated need, a need that best meets the functional, performance, and budgetary needs of the stakeholders. As noted on the previous slide, the DoD Initial Capabilities Document, or ICD, is by definition a validated set of needs. Hence, it is a requirements document. The needs are validated by the gap analysis. The gap analysis results should not be considered requirements. The gap analysis looks to see if the gap can be closed. The technology explored in the gap analysis do not need to exist at the time of the analysis, and in closer examination may not be affordable at the acquisition decision point. A national TV commercial asks, why pay twice as much for 1% more? That should be the ultimate goal of the analyses we undertake. So each of the types of analyses we've examined should be examined with respect to cost. We can plot each instance of a simulation run on a Pareto chart. Each color of the chart represents a different architecture. Each dot represents a particular run of the simulation. Each case run for any of the simulations we use in our analyses. We can create the sufficient frontier, the line that follows the outline of the different cases, for each of the architectures examined. Find the knee in the curve to find the point that gives us the best bang for the buck. That is the winning architecture. So, how is this all applied? This is a simplified extract from the JCIDS of some key milestones in the analyses that drive them. The first step in the process is the gap overlap analysis. This analysis establishes needs that form the basis for the ICD. The analysis is usually an effectiveness analysis since you're assessing the needs of the mission. These needs are documented in the ICD. The identified gaps can be addressed with non-material changes or result in developing material solutions. Organizations begin exploring means of filling in the gaps, and numerous concepts are explored. The Material Development Decision, or MDD, determines whether a material solution is needed and schedules an AOA. The material solution concepts are generally based on development insight and SME guidance. Insight refers to stakeholder preferences on kinds of solutions, for example, a low-cost solution or a complete solution or an affordable one. These architectures are generally matured using performance analyses. The concepts are documented as the could-be architectures. The could-be architectures are tested in the AOA. The AOA might use a combination of effectiveness, utility, performance analysis. depending on the complexity of the systems, the missions to be accomplished, and the range of the concepts. The results of the AOA are documented by the should-be architecture. The should-be architecture forms the basis for the capabilities description document or mission requirements document. Milestone A is a decision point that determines whether the new system will be purchased. Concepts are developed by the contractors that provide most affordable solutions to fulfill the CDD. In theory, the contractor offerings are assessed using effectiveness analyses, and the winning concept results in the to-be architecture and a capabilities production document or system spec. Milestone B is after the critical design review and determines if the system will be built. Additional analysis is performed throughout the development to ensure the system meets the CPD requirements and also that the system can operate in an ever-evolving hostile environment. We can summarize the taxonomy for modeling, simulation, and analysis here. The three types of analysis: the measures, the models we employ, and the scope they cover for good measure. Don't forget to create an analysis plan. Prepare it like a college lab experiment. Include an authoritative mission statement to define what you're analyzing. Include scope of the analysis. This will guide the analysis and manage expectations. Perform task, MOO, MO, MOP mapping to show what is being proposed satisfies the mission. Perform MO or MOP mapping to show that the model or which model can accomplish the analysis. Record the limitations of the analysis to help decision makers in deciding if the analysis satisfies their concerns. Define the cost measures involved. Again, this is part of the decision-making process. Are you balancing upfront cost versus cost avoidance? Show some expected plots. This helps elicit valuable input from decision makers on what they might want to see in the results. Include some definition of the could-be architectures that will be included in the analysis. In summary, apply the right level of analysis to make informed decisions. Performance is not effectiveness, and use analysis to accomplish various tasks. Reap the benefits of ms&a to provide documentation for the validation of concept or design, to reduce technical cost and schedule risk. I've included a few references if you're inclined to read further.